let's talk a little bit more about the derivatives of logarithmic functions and look at some more interesting examples. So the derivative of a logarithmic function, let's start with the natural log of x, is 1 over x when x is greater than 0, but we can extend that if we have the natural log of the absolute value of x. And the derivative of log of any base a, is going to be 1 over x times the constant ln of a. So those are the two derivatives that we're going to be working with, and we can look at lots of fun examples in this video. So let's get into these examples. So starting with this one, let's find the derivative of the natural log of the square root of the sine of 2x. So by the way, there are lots of nesting happening here. And so we are going to have to definitely use chain rule, and we're going to have to apply chain rule, repeated chain rule, because we have several nestings going on here. So let's go ahead and do it. I'm going to go through this, and then I'm going to show you a slightly different way to do this problem. So let's just jump right into the derivative and look at 1 over the square root of the sine of 2x. Then we have to take the derivative of the square root. So we've got 1/2 times the sine of 2x to the minus 1/2, power rule. Then we have to take the derivative of the next layer, the next inner function, which is sine. So we get cosine of 2x. Then we have to take the derivative of 2. So as I mentioned, multiple layers there, so we peel away the layers with chain rule. Then we keep going and do our simplification now. I see the 2 and the 1/2 are going to cancel, and we've got 1 over the square root of the sine of 2x times another 1 over the square root of the sine of 2x, coming out of that negative 1/2 dropping down. And then we have the cosine of 2x. So that, of course, is going to become the cosine of 2x over the sine of 2x when we multiply the two square roots together, and our final answer, cotangent of 2x. So our derivative is the cotangent of 2x. Now, I just want to mention, and I don't know if we would want to have done it this way, but it might have made our work a little easier if we had remembered some rules of logarithms. So let's just real quick look at another way we could have started this problem. We could have actually applied rules of logs, I'm going to abbreviate the word logarithm, rules of logs at the start to simplify. And this is a strategy that I want to explore a little bit more in this video, and we can start with this one where, maybe it's not the biggest time saver on this particular problem, but it can be. So rules of logs, we have rules of logs, and I'll project all of them because I did have them in this video. I did have them in the lecture notes typed up. So I'll project all the rules of logarithms. But before we go into that part, when we have a power, when we have a logarithm raised to a power, that power can come to the front as a constant. So this is equivalent to saying 1/2 times the natural log of the sine of 2x. And so simply by doing that, I have converted that root, just using rules of logarithms, I've converted that root into a constant multiple. And taking derivatives of constant multiples is easier than taking derivatives of roots. So now watch, by simply doing that quick little simplification at the start, now when I take the derivative, I'm taking the derivative of a constant 1/2 times the natural log, which will be 1 over the sine of 2x, times the derivative of the sine of 2x, which is the cosine of 2x, times 2. So again, same steps, but I was able to simplify the root using rules of logarithms before ever taking a derivative, and that did make my work, in this case, slightly easier, but it can sometimes make our work significantly easier. So it's a strategy we want to remember. So again, we end up with cosine 2x sine of 2x. And of course, that is the same simplification, we had cotangent of 2x that we had when we did it our first way. So, just, it's not like it was a huge time saver, but it was a nice simplification to do and did make the work slightly easier. So let's talk about a case where we might want to look at an example where we might really want to employ this idea of applying rules of logarithms before taking derivatives. So let's review the rules, and then I'll show you a case where we would definitely want to remember our rules of logarithms. Okay, so here's the algebraic rules for logarithms. When we take the logarithm of a product, it is equal to the logarithm of a plus the logarithm of b. I have written all of these rules with the natural log because that's the one we're going to utilize the most, but these rules are true for logs of any base. So let's make a little note right here. These rules hold for log base a of a as well. Let's write that actually of x as well. Important to remember, because if you ever come across a common log, you can also, of course, use these rules to simplify common logs as well. So products break out into sums, quotients into differences, and a power into that constant multiple. That's the one that we just used, where we pulled the power down as a constant multiple. So these are the rules. Again, these are coming out of pre-calculus. These are rules coming out of algebra, but we're going to employ them here in order to make our work in calculus a little easier. So now let's look at an example where we would definitely want to do this rather than try to just, bang our head against a crazy chain rule. So let's look at one of those. Okay, so let's take a look at this guy. Y equals the natural log of this giant e to the 5x times the sine of 3x all over 2x to the 5th minus 7x plus 1. All of that raised to the 5th power. Okay, let's take a little breath here and take a look at this. Do you want to go at this guy with the chain rule, quotient rule, product rule? Look at all of the layers, right? Like we've got a power, right? We've got a logarithm, so it's going to be 1 over all of this to this power. Then we're going to have to do the power function. Then we're going to have to get inside here, and we're going to have to deal with this, which is, by the way, a quotient, but with a product in the numerator. So we're going to have to be doing quotient rule and product rule within quotient rule. Whew, I mean, just even talking about it, I haven't even started taking the derivative. Talking about it is feeling like I might be here for a couple of days. So let's take a minute and let's pull back and let's think about it. And this logarithm right here allows us to simplify this so much in the beginning that our derivative actually is not going to be that difficult. So what do I mean by that? Well, I'm just looking at it, and the first thing I see is that power of 5. And so I am definitely, let's make a little start. I don't have to. I mean, I could plug and chug my way through it like I just mentioned, but let's make a little star and say use rules of logs to simplify, before I even take a derivative, to simplify before finding dy dx, before finding the derivative. And so I'm definitely going to do that. I look at this and I think, oh my goodness, like thank goodness there is a logarithm because I can simplify. So first thing, I see that 5, so I'm going to bring the 5 down in front, and then I've got the natural log of e to the 5x times the sine of 3x all over 2x to the 5th minus 7x plus 1. But what logarithms also allow me to do is they allow me to break up a quotient into a subtraction. So I'm going to erase that, and I'm going to write, okay, so it's 5 times, it is 5 times all of this. It's 5 times e to the 5x times the sine of x minus the natural log of 2x to the 5th minus 7x plus 1. Okay? And logarithms also allow me to break up products into sums. So one last line, let's write this as 5 natural log of e to the 5th. Oh my goodness, look at that. That's going to simplify nicely too. Natural log of the sine of 3x minus the natural log of 2x to the 5th minus 7x plus 1. And look at this piece right here. This guy even simplifies further since it's natural log of the same base e to the 5x. This is simply 5x. And so now we've got, I'm going to distribute the 5 actually. So it's 5x times 5. So this whole thing right here becomes just 5x, and I'm going to go ahead and distribute the 5. Before I take a derivative, by the way, I have not taken a derivative, no prime notation, no dy, dx. I am just simplifying using the rules. So be real careful, remembering when you're simplifying, when you're taking derivatives, and we haven't taken a derivative yet. So this became just 5x, so that's going to be 25x plus 5 times the natural log of the sine of 3x minus 5 times the natural log of 2x to the 5th minus 7x plus 1. And now I can take the derivative of each of these terms, and the derivatives, I still have to apply chain rule to 2 of those terms, but the derivatives are far easier to deal with than they were at the beginning up here where we started. And so now let's take the derivative. So now take the derivative of a much simpler function. So now take the derivative. And let's get in here, and the derivative dy dx, or y prime, is going to simply be 25 for that first term. For this next term, it's going to be 5 times 1 over the sine of 3x times the cosine of 3x times 3. And then minus 5 times 1 over, looks like a decimal, 5, let's write it like that, 5 times 1 over that whole thing, 2x to the 5th minus 7x plus 1. Then we have to multiply by the derivative of that, which is going to be 10x minus 7. Okay. And simplifying that out, we're going to get 15, 3 times 5, and then I have cosine over sine, so I'm going to write that as cotangent of 3x, and then I have minus, let's go ahead and distribute the 5, so I've got a, well, I don't know, maybe we don't want to, maybe we want to leave it. Either way, you could either distribute the 5 or leave it. Let's leave it. Let's leave that common factor factored out. And there we go. Now, remember at the beginning, it was like when I first even just read it out, like thinking about taking that derivative with that multiple layers of chain rule and quotient product within a quotient and power. I mean, whew. But look at, this was really, I mean, the derivative literally was like a one-liner, right? We did one line and then a line of simplification, and that was pretty simple. So remember your rules of logs. They will come in handy if you have a function that has a logarithm. But what if we don't have a logarithm and we have a crazy function that we want to work with? Let's talk about another strategy that we could use. Okay, so we've just talked about how useful it is to have a logarithm so that we can use the logarithmic rules to simplify a function before taking the derivative. But what if I come across something like one of these two, right? Like there's no logarithm, right? Like I wish there was a logarithm right here, but there's no logarithm right there. And so what can I do about this, right? Like I'm just going to have to, bang my head at it, right? And use chain rule and product rule within quotient rule. And, it was very similar to the one we looked at a second ago, where we've got this product and we've got this in a quotient and we've got a power. The only thing is we don't have the logarithm, so we can't actually simplify it. Well, what about something like this? We have no way to do this. We have never encountered something of this nature, and we don't have a rule for taking the derivative of a function to a function. Notice that this is not an exponential because the base is variable. This is not a power function because the exponent is variable. So this is a function to a function. So what in the world are we going to do with this, right? How am I going to deal with a function to a function? Because it's not of a form that we know how to take the derivative of yet. And this is where we get this other technique called logarithmic differentiation that actually is going to allow us to introduce a log to both of these, because both of these functions, if I had a logarithm in front, right, if I had this logarithm, now it doesn't exist there in the beginning, but if I had a logarithm, this would simplify, and if I had a logarithm on this guy, I could actually take the derivative because it would become a product rule. So if I were to introduce a logarithm right here, notice what would happen. I could pull that x down and it would become x times the natural log of the sine of x. So if I had a logarithm, and that's the key, I don't, but if I had a logarithm, both of these two functions would be, the first one easier to differentiate, and the second one I would actually be able to differentiate, because right now I cannot differentiate it. So how do I get that log in there? Well, I am actually going to introduce a log, but I can't just put it into a function without changing the function. So when I do this process, which is called logarithmic differentiation, I'm going to have to introduce a logarithm to both sides of the function. So let's write up some steps. I'm going to take this one and we'll do this one second. So I'm going to move it down below and I'm going to write some steps up as we go. So and then in the end we'll formalize it. So this is a process called logarithmic, and it comes in really, really handy. So logarithmic differentiation. So logarithmic differentiation, what we're going to do is, the general idea is we're going to introduce a logarithm to a function so we can simplify using rules of logarithms. Simplify using rules of logs. So that's the general idea. Now, this idea of introducing a logarithm, well, what we're going to do is we're actually going to take the natural log of both sides of the function. And then, in order to take the derivative, we will actually have to use implicit differentiation. So we're going to have to pull from, a couple of our tools out of our toolbox, but we're going to put those things together and it will help us to take derivatives a lot easier. So let's go ahead and write out these steps and do it. We are going to start by introducing that log. So we're going to take the natural log of both sides of the equation or the function, what is given to us as a function. But it could be otherwise. So these are given to us as a function. So we are going to take the natural log of both sides. I just noticed that this guy. So we're going to take the natural log of both sides. I'm going to go ahead and, just for purposes of making it easier, I'm going to go ahead and write this as y instead of f of x. So I'm just going to go ahead and replace the f of x with y. So we're going to let y be equal to f of x so that I can work with a y rather than always writing f of x. And then I'm going to take the square root because I have to work on both sides of this equation. So that is going to make it easier. Cosine of x, and I'm going to introduce that logarithm on both sides of the equation. So I've got the natural log of both sides. So now remember, just a minute ago I had said, shoot, what if we had just had a logarithm for the square root? It would make things so much easier because I can simplify using the rules of logs. Well, that's actually what I'm going to do now. So the second step to logarithmic differentiation is to simplify completely using rules of logs. So simplify completely using rules of logs. So we're going to get in here and we're going to do exactly like we did on the previous example. Instead of a square root, let's think of that to the 1/2 power. And since it's to the 1/2 power, I could pull the 1/2 out in front. We're just going to leave that natural log of y on this side of the equation for now. And we're going to get 1/2. Now, when I do that, when I take the 1/2 down, then I can also break apart the quotient So this quotient right here, I can break apart the quotient as a subtraction, and the product in the numerator I can break apart as a addition. So I'm going to go ahead and do all those steps at once, but I'm just applying my rules of logs. So I have natural log of 5 to the x plus natural log of 2x minus 7 to the 11th minus the natural log of the cosine of x. Okay. I'm running into my steps a little bit on this small screen, but that's the idea. I'm going to actually keep going. I am going to simplify just a little bit further because I see this x right here, and so I'm going to just make that x times, so I'm actually going to leave the 1/2 out in front. 1/2, and we're going to get x times the constant natural log of 5. That's, by the way, just a constant. Plus, I'm going to pull down this 11 too. 11 times the natural log of 2x minus 7. Nothing to do on this last one, so minus natural log of the cosine of x. Okay. Now what we're going to do is we're actually going to differentiate, but we're going to differentiate with implicit differentiation. So because our y is embedded, right? Our y is inside of a function right here. And so, and to get rid of it, I would have to, exponentiate both sides of this. And so I'm going to leave it like that, and I'm going to take the derivative. I'm going to take the derivative using implicit differentiation. So this is what I mentioned. Logarithmic differentiation is a very powerful tool, and it really is just putting together a few of our previous mathematical tools, rules of logarithms, and implicit differentiation. So our third step, and I'm sorry my steps are kind of running together, but I'll squeeze it down here. My third step is now to take the derivative implicitly. Implicitly to find dy dx. So we're going to come in here, we're going to take the derivative of both sides of this equation. The right side is all in terms of x. The left side is going to be 1 over y times dy dx. Now, the right side of this equation, when I take the derivative, we've got that constant. And the derivative of x is simply 1. So this is just natural log of 5 plus, we're going to have 11 times 1 over, I'm going to do a couple steps at once. I'm going to have 11, and then it's going to be 1 over 2x minus 7 times 2. So I'm going to go ahead and write it like that. I'm going to write the 1 over. We had that constant 11. I'm going to put it in the numerator and the times 2 in the numerator. Then the derivative of the natural log of the cosine of x. So that's going to be minus 1 over the cosine of x times negative sign. So I'm going to put that negative sign also in the numerator. Okay, not a whole lot to simplify, but let's get 1/2 natural log of 5 plus 22 over 2x minus 7. This becomes plus the tangent of x. Now over here we still have 1 over y dy dx. So we still have to solve for dy dx, but this is easy to solve for dy dx. I just have to multiply both sides by y. So I'll multiply both sides by y, and then I find that my derivative dy dx equals this right-hand side. But let's focus on that for a second. What is y? Well, I know what y is. Y was what we started with, right? Y was this whole thing. So I can just put that in. So I end up with 1/2. My last step is I'm going to back substitute in y. So I'm going to end up with 1/2 times the square root of, 5x times 2x minus 7 to the 11th over cosine of x times, and by the way, I put the 1/2 out in front, times natural log of 5 plus 22 over 2x minus 7 plus the tangent of x. And I was able to find that derivative without having to do, all of those crazy layers of chain rule and simplification. Okay? So even though I didn't have a logarithm to simplify it, I could introduce one and then I could pretty easily find the derivative after my logarithmic simplification. Okay, so that's the basics of logarithmic differentiation. We're going to introduce a log, take the natural log of both sides of the equation of the function, simplify it completely using the rules of logs, and then take the derivative implicitly to find dy dx. This last step will involve, in the end, substitute back in for y at the end. Okay, at the end of your implicit differentiation, you do want to substitute back in for y, just like we did. That's what we did right here. We went back and we put our y back in after we had solved for dy dx. Okay, we're going to do that other example here in just a second, but I actually have this formalized, so let me go ahead and show you that screen, and you can take a screenshot or take down notes on the steps for logarithmic differentiation. So here are the steps for logarithmic differentiation typed up. So the idea again is to take the logarithm, natural log of both sides of the equation. You could actually, I guess, use log of any base, but natural log works out the nicest because of the derivative being just 1 over x without that constant. So take the natural log of both sides of the equation. Use the rules of logs to simplify. Break it apart as much as you can. Break apart your products, your quotients, bring down your powers. Use those rules of logarithms to simplify. Then take the derivative of the more simplified version of the equation using implicit differentiation. But that left-hand side, here's the piece, right? That left-hand side will look like this because you've taken the logarithm of the function, the logarithm of y. So you'll have that 1 over y dy dx. Then just solve for dy dx and substitute your y back in at the end. So that you have your final answer. Okay, so again, useful strategy. Sometimes just in order to simplify a function that we want to break down a little bit before taking the derivative, but it is not just useful in that case, sometimes it is necessary. So let's go look at that y. This is a process that we have to use for, let me put this here, we have to use logarithmic differentiation for functions of the form y equals f of x to the g of x. So this is necessary for y equals f of x to the g of x. The last one we actually could have done using our other methods, but for something, a function to a function, we have to use logarithmic differentiation to find the derivative. Okay, so here is one of those, functions to a functions. We don't have the tools because this is not an exponential and it is not a power function. We have variables in, right, both the base and the exponent are variable. So it is neither exponential nor is it a power function. So we have to use logarithmic differentiation to do this. So we will take the natural log of both sides of this equation. This side will become the natural log of y. This side, because of that power, I can pull it down. This will become x times natural log of the sine of x. And now, all of a sudden, I can take the derivative because I no longer have a function to a function. I have a product. So notice right here, I have now, simply with those rules of logs, created a product, and I can take the derivative. So we'll take the derivative of both sides, do it implicitly. So taking the derivative, we're going to end up with 1 over y dy dx. This side we have to apply product rule, so 1 times the natural log of the sine of x plus, continuing with the product rule, now we'll take the derivative of the natural log of the sine of x, which is going to be 1 over the sine of x times the cosine of x, so I'm going to put the cosine of x on the top, times x. Now, that, of course, is the cotangent, so we could write that as x times the cotangent of x. And here we just have the natural log of the sine of x. And over here, I'm going to leave that all in a bracket, because on the left side of the equation, we just have to solve for dy dx. So all we have to do is multiply by y. So we just have to multiply both sides here by y. And so dy dx equals y times the natural log of the sine of x plus x times the cotangent of x. But y is just the sine of x to the x. times the natural log, and I'll just bring the rest of it in, natural log of the sine of x plus x times cotangent of x. And there's our derivative. And we found it using that super nifty process called logarithmic differentiation. So logarithmic differentiation is a process, a technique, a tool that you want to keep in your toolbox, keep in your back pocket, right? Something that you can apply when necessary. And so those were two examples where we used it. One was one that we didn't have to use it on, but the second one we did. We absolutely needed it for that second example.